Hey everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. So this is the introduction to thermodynamics, and I want to start it off by talking about the difference between entropy and enthalpy. I'm sure you've all heard these terms many times before, and I'm sure you all think you understand it. But this is one of those really deep, meaningful things that even though you think you understand it, you can always go deeper and understand it on a better level. So let's talk about it. I'm sure that most of you have heard of entropy defined as randomness or disorder or chaos. That certainly makes a lot of sense. And then enthalpy you can think of really as just like energy, or some people would call it heat, the amount of energy put into a system or contained within a system. So let's look at these two systems. Here we have Tropical Storm Arlene on the left here, and on the right we've got Hurricane Katrina, both from 2004, 2005. So how do you know which one has more entropy and which one has more enthalpy? Now you know, because you know a little bit about hurricanes and about tropical storms, that Hurricane Katrina over here has higher wind speeds. It's got a lot more rain falling. It's got a lot going on, whereas Tropical Storm Arlene over here probably has lower wind speeds. So that right there, the strength of the wind and the amount of precipitation would probably tell you, first of all, that Katrina probably has more energy and therefore more enthalpy, and that's totally correct. And then you might be able to guess that Tropical Storm Arlene has more entropy, just by virtue of the fact that frequently systems that have a lot of enthalpy are low in entropy. Not always true, but sometimes. Now, very frequently, people in this example will get confused because they're thinking not so much of the storm itself at this moment in time, but they're thinking about what happens after the storm. And certainly it's true that after Hurricane Katrina rages through, Mississippi and Louisiana, it leaves behind a path of destruction that consists of a lot of entropy. Homes and buildings smashed and torn apart. Yeah, that's entropy. But that's after Hurricane Katrina moves through. Right now, we're considering just this moment in time when these photographs were taken. So Hurricane Katrina has much more enthalpy, and Tropical Storm Arlene has much more entropy. How do we know? Well, we talked about the wind speed and the rainfall patterns, but the other way that we could think about this is in terms of things like symmetry. Right? A system that has a lot of symmetry has order to it, and therefore it is not random. It does not have entropy. And you can see Hurricane Katrina here has a very well-defined eye wall. It has a lot of radial symmetry, right? We could draw planes of symmetry, actually an infinite number of planes of symmetry through this storm, and it would be roughly symmetrical about that plane of symmetry. Whereas Tropical Storm Arlene over here, I don't know, it's really good. It doesn't have any symmetry at all. Maybe a little. You can see some bands of clouds here that are probably wrapping around, but not a ton of symmetry. And the other thing we might think about is gradients. Okay, so here it's very clear that this is not part of the hurricane, but this is definitely part of the hurricane. There's a strong gradient in moisture concentration in the atmosphere. Basically cloud vapor. There's a big gradient between here where there's virtually none and over here where there's a whole lot. Whereas for Tropical Storm Arlene, it's a little bit tougher to define whether this area right here, for example, is part of the hurricane or not. Maybe it is, maybe it isn't. The gradients in the water vapor concentration, the gradient in wind speed, the gradient in barometric pressure, the gradient in rainfall, all of those are much stronger and more intense for Hurricane Katrina, where you go from nothing, from a higher temperature, lower wind speed, less water vapor, to a zone of very high, lower temperature, higher wind speed, and higher water pressure in a short period of time, in a short period of space. You have a strong spatial gradient. So things like symmetry and gradients are important things to look for when you're asking yourself, what's entropy and what's enthalpy. So let's look at some examples. So here's an example of our friend benzene. I'm going to talk about benzene a lot in this class because, it's a very common chemical. Benzene has radial symmetry. It's got actually 12 planes of symmetry, like here, 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 and here. So 12 planes of symmetry, plus it has a plane of symmetry that is in the plane of the molecule, basically in the board here. That's a plane of symmetry. So it's got a lot of symmetry. Here's cyclohexane, which has got the same number of carbons, but remember cyclohexane can have this boat conformation or the chair conformation. And so it has fewer planes of symmetry. It has a plane of symmetry here. This one does, but this one, I don't really know. I guess it's got a plane of symmetry running basically from this point to that point, but not a ton of symmetry, and it has more than one conformation, whereas benzene is totally rigid and cannot flex and have these different conformations. So that tells you benzene has less entropy. Hexane, of course, we've drawn it here as a straight line, but in truth, hexane can have different conformations. Like this carbon here could stick down this way, right? This could go this way. They can all these bonds can turn and flex, and so you can have different conformations of hexane. So this has got a lot of conformations. Cyclohexane only has 2, but hexane itself has tons. It's constantly sort of writhing like a snake, so it's got a lot of different conformations, therefore more randomness, more entropy. In terms of enthalpy, it's not immediately obvious or maybe not intuitive, but benzene has much more enthalpy. You can see here's the heat of formation for benzene, much, much higher than it is for cyclohexane and hexane. So that's an indicator that you had to put energy into the system in order to drive a system toward lower entropy. That's frequently the way it works, not always, but frequently. In order to force a system to have less entropy, you're going to have to put energy into it, and therefore you're going to have a high enthalpy, low entropy system. Again, not always, but frequently. Okay, here's another example of something you might call, it's not really a reaction, I don't know what you want to call this, but I'm going to call this just, sorting. So if you have a bin full of different colored marbles over here, and you sort them into the different colors, over here, this system has low entropy because now you've sorted these out, and this system has much higher entropy. And you could think of this as a gradient, right? The concentration of the purple marbles here is 1 purple marble per marble, 1 to 1, whereas over here it's only 1 purple marble per 10 marbles. So it's got a lower concentration of purple marbles. And the act of doing this sorting, this child is adding enthalpy to the system at the time that they're decreasing the entropy. This child, this poor manual laborer here, is putting work into the system in order to drive it to a lower entropy state. So another thing that happens frequently, a chemical reaction, is these kinds of reactions where you have a dissociation. You're starting out with 1 molecule and you're ending up with basically 2. In this case, they're ions, but you get the point. You have one thing, we'll call it a particle. It's not really a particle, but let's call it 1 particle, and it dissociates into 2 particles. 2 particles flying around has more entropy than just 1 particle flying around. It's like when you get divorced. 2 single people have more entropy, more randomness, more chaos than 2 people that are married and are always stuck together, for 9 months in the same house under lockdown, under COVID. So those are some more examples. Here's another example. Here's some chemicals in the gas phase at the top and also at the bottom in the condensed or liquid phase. And in this system, if you're in the gas phase, this chemical right here is interacting with basically just empty space. This is all just, it's a void. It's literally nothing. It's just empty space. And so in a sense, this chemical is interacting with nothing. It's not really interacting with other chemicals at all. Occasionally it will have a collision and there will be some, something going on there, but it has a lot of freedom to move around. The gas phase is mostly nothing, right? But when this same chemical now dissolves in the water here, or whatever this is, this happens to be water, now it's constrained. It's got water molecules all around it. And it's like being at a party where there's just tons of people all around you and you can barely move to get to the, to the keg. You remember, when we used to go to parties? Yeah. And there are people and you could touch them. So once you're in that condensed phase, you have much less entropy. This molecule has much less entropy in the condensed phase than it did in the gas phase. So that's important to us in the environment when we think about things like Henry's law, which is the partitioning between the water and the gas phase, and also just vapor pressure, which is where a liquid vaporizes into the gas phase. So we need to consider this. So the gas phase has much more entropy, and then not surprisingly, it takes energy to get things into the gas phase, so it has more entropy, but it also has more enthalpy. It took energy to get it there. So that's an example of where entropy and enthalpy are not always diametrically opposed. Couple more quick examples. In the environment, we very frequently have gradients. Here's an example from the surface of the ocean. At the surface of the ocean, you tend to have wind-driven currents here, and that causes a fair amount of mixing. And you also have some fresh water that comes in from, the land all over the earth. And so the density in the red here, the density is a little bit lower at the surface because you have some fresh water that's mixing in. But down here at the deep ocean, the density maxes out and then pretty much just stays constant with depth over a long period. And conversely, you've also got the temperature, which is in blue here. Temperature tends to be higher at the top of the ocean because there's, solar energy, solar radiation that's heating up the water. But at some point, that kind of goes away and you're left with very cold ocean water here down at the bottom. And so this area where there's this rapid change in salinity as well as in density, that's called the picnic line. And you can imagine that because there's wind-driven currents up here, this part is fairly well mixed and therefore has higher entropy. Whereas down here, there's just not a lot of energy available for mixing, and so this is a little bit of a lower entropy system. And because there's a good amount of mixing here, there's all kinds of stuff that have a gradient. It's not just the temperature and the density, but also things like oxygen. Carbon dioxide has a gradient. Any gases that are coming in from the atmosphere, and it doesn't even have to be gases, anything that's coming in from the atmosphere is going to have a higher concentration up here in this mixed layer than it does deeper in the ocean. So you're going to see gradients not just in temperature, salinity, things like that, but gradients in the concentrations of all kinds of different species and all kinds of different chemicals and also species. Phytoplankton can choose where in this water column they want to float. They can swim a little bit and make some decisions about where they want to be. So that's an example of a real environmental system where you can think a little bit about the entropy and the enthalpy. So again, this is a little bit of a lower entropy system down here, and because it's colder, it's also got less enthalpy. Similar kinds of stuff goes on in the atmosphere. So these are just a couple of pictures that I found to kind of illustrate the atmospheric boundary layer. You've got some cities here that are churning out pollution. So this orange stuff is pollution. And you can kind of see here, I don't know how well you can see this, but this is the atmospheric boundary layer here. Right about there, there's a boundary layer. So below it, the air is reasonably well mixed because it's got solar energy that heats the land. Then the land heats the air and the air rises, but then as it cools, it drops back down. And so you get this convection that mixes the air in this lower part of the troposphere. But then up here, the temperature is fairly constant and there's not as much mixing. So similar things. And then this is just showing a very similar thing. You can see where the clouds there's an atmospheric boundary layer here, and there's clouds below it, or fog, or I don't know what it could be. Could be pollution, could be fog, could be clouds, but it's below that atmospheric boundary layer, and above the boundary layer, it's relatively clean. So that's an illustration of some examples of entropy and enthalpy. Again, down here where there's mixing, there would be more entropy, but there would also, in this case, there's more enthalpy because it's generally warmer down here and colder up here.